In this lesson, the focus is boiler startup and servicing and hydronic radiant heating. The big theme is pretty simple. Follow the manufacturer's process, verify safety devices, and keep water quality under control so the boiler and the radiant system last. The module's rationale is that safe, reliable hydronic heat depends on correct commissioning and ongoing service. The outcome is being able to install and service residential radiant floor hot water systems, and the objectives break into 4 areas: startup, boiler service, control service, and basic radiant system maintenance. A key idea is that boiler startup is manufacturer-specific. The manual typically walks through pre-installation inspection, unpacking, water piping, gas piping, venting, electrical, system startup, then service and troubleshooting, and finally repair parts. The safest approach is to treat that manual like the primary checklist. Pre-installation is about preventing predictable hazards. Inspect for shipping damage, confirm required clearances to combustibles, both manufacturer minimums and local code, ensure proper combustion air and venting plan, set the boiler on a level surface, and keep it away from flammables, chemicals, and any water that could drip onto ignition components. Unpacking sounds basic, but it matters. Boilers are created with bracing and hold downs, and manufacturers usually specify the removal sequence so nothing twists or falls. Once the crating is off, then the unit can be moved safely to its final location. Water piping is critical because wrong piping can damage the boiler or the building. Manufacturers warn about low flow and cool return water, especially on boilers not designed for it, and about oxygen contamination that drives corrosion. The piping layout also needs the safety relief valve and proper control locations, plus air elimination, expansion handling, isolation, and service drains, exactly as the manufacturer's piping drawing shows. After piping is complete, the system needs to be flushed to remove oils, grease, and debris. Then water quality has to be protected with appropriate chemicals because high oxygen content and contamination corrode steel components and can void warranty coverage related to oxygen contamination. Good water is not optional in hydronics. On the gas side, the line must be sized correctly and meet gas code. When pressure testing, the boiler should be isolated and the piping tested for leaks. Leak checks are done with an approved gas detector or a soapy water test. Simple, visual, and effective. Manufacturers also show the required isolation valve, sediment trap, and union arrangement. Venting must follow the authority having jurisdiction and the manufacturer's vent material and sizing requirements. After venting is installed, a spillage test is performed. Run the main burner at least 5 minutes, then use a match, candle, or smoke tester at the draft hood entrance. The flame or smoke should be pulled into the draft. If it spills out, something's wrong. Electrical wiring has to comply with the electrical authority and code. Manufacturers provide both schematic and ladder diagrams to show internal boiler wiring and to guide wiring for thermostats, zone valves or pumps, circulators, and safety devices. One common pattern is 120 volts feeding the boiler and circulator, and a transformer stepping down to 24 VAC for controls like the gas valve and thermostat circuit. System startup begins with filling and venting air. Radiant floors have lots of tubing, so trapped air can be stubborn. A common approach is to isolate all zones, connect a hose to a boiler or manifold hose bib, open the fill, then open one zone at a time, usually starting with the closest. Purge each loop until bubbles stop, then keep going briefly, close it, and repeat. After all zones are purged, set system pressure with the pressure-reducing valve, open zones, run pumps, and let air vents finish the job. Before firing, gas codes require trained personnel. The burner must be properly secured, then standing and operating gas pressures are checked with a manometer. Clocking the appliance verifies input matches the manufacturer specs. Final connections get soap tested, and both pilot and main burner flames are visually inspected per the manual. Operational checks are essentially proving the sequence of events. Raise and lower the thermostat to force a call for heat, and then satisfaction. Verify ignition and main burner operation. Then test safety shutdowns like low water cutoff and flow switch. These must stop fuel if there's low water or no flow. Finally, verify the temperature control. An aquastat or thermistor-based control actually cycles the burner and then gets set back to the desired temperature. Manufacturers usually include troubleshooting built around a sequence of events chart. What should happen, in what order, when there's a call for heat. When a boiler won't start, that sequence helps pinpoint where the chain breaks. And for repairs, the manual's exploded parts drawings and part numbers make ordering the correct replacement much faster. Service and inspection should be done at the beginning of every heating season. The first step is always shutting off electrical and gas supplies. Then confirm the area is free of combustibles and flammable vapors. Check safety controls, inspect venting for blockage and deterioration, clean flue passages as needed, and remove and clean burners and the firebox, typically with a vacuum and soft brush. Many boilers need access panels, or even the jacket top or canopy, removed to clean properly. The goal is to remove soot and blockages from the flue passages and ensure the venting path is clear. Burners are cleaned gently, vacuum and soft brush, because damaging ports or components can create combustion problems. On the combustion side, service includes checking orifice passageways for blockage, cleaning the pilot orifice and line, and evaluating the thermocouple condition on standing pilot systems. After reassembly, the pilot is lit, the thermocouple is tested and replaced if needed, and standing and operating gas pressures are verified and adjusted if required. Then the boiler is restarted and flame and control operation are confirmed. For controls, the key foundational tests are continuity and resistance. Continuity proves there's a complete electrical path, often just whether switch contacts are open or closed. Resistance is measured in ohms. The critical rule is power must be off, and the component should be isolated from the circuit before doing continuity or resistance testing. Electronic controls often use thermistors. The controller interprets resistance as temperature. Here, higher resistance means lower temperature, and as resistance drops, temperature rises. When a controller can't read a sensor, the troubleshooting path is to test the controller terminals, the wiring run, and the thermistor itself, isolating and testing each part separately. To use a thermistor table, convert the meter reading properly. If the meter is on kiloohms and reads 16.41, that's 16,410 ohms. Then compare it to the resistance table to estimate temperature. In this example, it lands between 55 and 60 degrees Fahrenheit. Room thermostats need little maintenance, but they should be checked before heating season. The module emphasizes not using a thermostat with a heat anticipator for hot water systems. Anticipators are meant for forced air and can shut the boiler off early. Service is mostly inspection, wiring condition, tight terminals, clean sensing elements, and confirm calibration accuracy. Liming controls like aquastats are maintained much like thermostats. Inspect wiring and terminals, clean contacts, and verify calibration. Also inspect the capillary tube and sensing bulb, because damage there can cause incorrect temperature control or a failure to respond. A float-type low-water cutoff protects the boiler from firing when water level is too low. If contaminated water causes the float to seize closed, the boiler could keep firing during a low-water condition, risking serious damage. The test is straightforward. With the burner running, isolate and drain the LWCO so the float drops. The main burner should shut down. If it doesn't, shut the system down and clean or replace the LWCO. Flow switches prove that the boiler has the required circulation. With flow, the paddle moves and closes contacts. Without flow, it opens, and the burner should be disabled. Testing often includes running the burner and then stopping the circulator. Burner should shut down. If not, turn off the gas and investigate paddle tension, contact condition, and whether contamination is causing the paddle to stick. Transformers step line voltage down to 24 VAC for low-voltage controls like gas valves. Testing is done with a multimeter set to AC volts. Measure the low-voltage side across R and C. If it reads 0, don't assume it's dead immediately. Check the primary side for line voltage. If the primary has power but the secondary is 0, then the transformer needs replacement. Spill and rollout switches are thermal snap discs meant to shut the burner down during unsafe combustion conditions. A spill switch reacts to hot flue gases spilling from the draft hood relief opening. A rollout switch reacts to flame rolling out of the burner area. Both work by temperature rise opening contacts and interrupting the safety circuit. Electronic controls usually require very little routine service. Many have self-test functions, and when something goes wrong, they communicate through a flashing light or an error code. The correct approach is to use the manufacturer's troubleshooting guide to interpret the code, then test the indicated circuit, often a sensor, wiring, or the control itself. For radiant floor heating systems, most maintenance centers on the boiler and the components around it: pumps, mixing valves, zone valves, and manifolds, plus water quality and water temperatures. Many modern components are designed for long life with minimal service, but the system still depends on correct conditions, especially clean, treated water. Water quality is described as the most important servicing factor. Untreated water drives oxidation of ferrous materials and sediment buildup that can foul pumps, mixing valves, zone valves, manifolds, and heat exchangers. Scale inside the heat exchanger reduces heat transfer, like insulation, which can overheat the exchanger and lead to cracking or failure.
Contamination can also plug tubing and circulators, causing low flow and overheating, and some polytubing systems can even support bacterial growth that reduces performance.
The recommended practice is yearly water checks, with chemicals added as required. A water sample can be taken to a company that analyzes hydronic water and supplies the right treatment chemicals. The point is reliability and efficiency. Proper testing and treatment prevents corrosion, scaling, and the cascade of component failures that follow. Glycol is used for freeze protection, often in slab-on-grade or snowmelt applications, but it comes with trade-offs. Propylene glycol is non-toxic and generally preferred where cross-contamination risk exists, while ethylene glycol is highly toxic and can be more corrosive at high temperatures. Any glycol system still requires backflow protection, and under high heat, glycol can break down, forming organic acids that lower pH, so inhibitors are needed. Many recommendations suggest isolating glycol from the boiler using a separate heat exchanger to reduce damage risk. Glycol should be added only when freeze protection is actually needed. The module highlights 4 decision factors: whether the building is left unattended, the risk of utilities being off, how long repairs might take due to location and parts availability, and whether the system is a snowmelt application. The glycol-to-water ratio must follow manufacturer specs. Common ranges are roughly 60-40 to 30-70. Too much glycol can gel and stop circulation. Too little may not protect at low temperatures. Glycol also reduces efficiency. It needs more energy to heat, it's more viscous so pumps work harder, and it expands more than water, often requiring expansion capacity to be increased by about 15 to 20%, depending on the mix. One way to add glycol to small systems is a side stream chemical pot feeder. The visual layout is basically a small vessel piped into the system with isolation valves, a fill point with funnel, and a drain. It's used when the system will be fully glycol water solution and you need a controlled way to introduce concentrated glycol. The typical pot feeder procedure is fill the system with water when temperatures won't freeze it, close the pot isolation valves, open the pot drain to relieve pressure and drain, close the drain and open the fill, pour in 100% glycol until full, then close the filler valve and open isolation valves while closing the boiler supply valve and pump to push glycol into the system. Then repeat until the required amount is added. The most common method is pumping a pre-mixed glycol water solution into the system. The pump's suction sits in the mix container, and the discharge connects to a filler valve or hose bib. As glycol is added, system pressure must be monitored to avoid overpressuring. If the glycol is in, but pressure is still low, the pressure-reducing station can be opened to top up to the correct setting. Cross-connection protection prevents non-potable boiler water from contaminating potable water. The authority having jurisdiction determines requirements, and standards commonly reference AWWA guidance. Hydronic water is treated as a severe hazard because of chemicals and additives, so a reduced pressure principle backflow preventer, an RP, is typically required, installed upstream of the pressure-reducing station, and it must be registered and tested yearly. Pump maintenance depends on pump type. Older pumps may require bearing or bushing lubrication and inspection of the spring coupler a few times during the heating season. Newer wet rotor circulators use system water for lubrication and typically need no routine maintenance, assuming correct installation and good water quality. Manual mixing valves can seize from poor water quality and lack of use, so exercising them regularly, about weekly, helps, and marking the original handle position ensures it goes back where it was. Zone valves usually require little maintenance. They cycle a lot and eventually the actuator motor fails, and the common fix is simply replacing the motor without shutting down or draining the system. Manifolds may need periodic checks for leaks, secure wiring to actuators, working air vents, and balanced loop flow, especially if occupants report hot or cold spots. Water temperature needs to be checked throughout the system. Cold return water to a non-condensing boiler can cause unnecessary damage and lead to failure. At the same time, the boiler supply must be hot enough to satisfy all loads, and the radiant floor supply must be controlled so it's not too hot entering the floor circuits, both for system protection and comfort. Before servicing, the module recommends talking with occupants. They're often the best source of symptoms like hot and cold spots or comfort complaints. After the work, create or update a service and maintenance log and leave it in the mechanical room. Recording original settings, changes, and parts replaced makes future troubleshooting faster and supports a preventative maintenance schedule. The takeaways are: start with the manufacturer's procedure every time, pipe and purge correctly so flow and air removal are solid, make gas, venting, and electrical code compliant and test them, prove the full safety chain and operating sequence, and for long-term reliability, focus on water quality, proper temperatures, and good documentation in a service log.